So now we've got the velocities of the particles in the normal direction that we've defined after impact. And now we just have to find the t direction. And if you saw that previous video on the on this oblique impact deal, right? We're going to apply conservation of momentum of each particle individually in the t. And the reason that we can do this is because, shoot, there's no exchange of forces in the t direction. In the t direction. All right, there's no interaction or no forces being exchanged, no impulses. Okay, and so here I've got here all I have really is just that VA of t is equal to VA prime of t, which means that this is still minus 6.46 meters per second. The velocities in the tangential direction are the same before and after impact. VB of t is equal to VB prime of t, and this is 2.77 meters per second. It's too easy, right? Two equations, two unknowns, and then you just know this. You have to understand this, right? And and now you have your velocities before and after impact. Okay, so I could go back up here, and I have essentially numbers for this. And if we go back and look down here, I've got, let's see, I have for VB prime event, I've got a minus 2.14. That means this VB prime event, this direction is actually going the other way right here. Okay. Okay, but before we jump ahead, let's talk about what the speed is. The speed is just combining the vectors, okay? So combining the vectors and getting the magnitude of the total vector. So the speed now, the speed of the particle after impact, so VA prime is equal to the square root of VA prime of t plus VA prime of n. This is the very popular square root of some squares, and you as an engineer are stars, and there's no issue, and you're going to do this, and this comes out to, let's see, for VA, I got here square root of minus 0.22 meters per second squared plus VA prime of n minus 6.46 square meters per second squared, and that comes out to, oh, 0.22 is such a small number. It essentially comes out to about, or a little bit, oh, if I carried some more significant figures, but it's okay. 6.46 meters per second, 6.47 maybe, and then VB prime, again, doing the square root of some squares of minus 2.14 meters per second squared plus 2.77 meters per second squared is equal to 3.50 meters per second. So we've got now the speed. Now we will also want to know the direction of these vectors after the impact. Okay, so here, and you want to know this because you want to know which way the particle is going after impact. So I redrew it after impact here so that I can have a better feel for what's going on here. But here, I want to draw. I have the center of each of my components here, or my particles here, and I want to know what direction they're going. So what I'm going to do is draw the components in the direction that they're supposed to be. So for instance, here, let's see, in the velocity of particle A after impact in the normal direction, I have negative 0.22 meters per second, which means that I go this way. It's about right here, and this is 0.22 meters per second. That's its magnitude. I don't need to put a negative sign because I've drawn it correctly in the right orientation, in the negative n direction. Okay, so here's the positive n direction is going upwards, the negative n, I've drawn it this way. And then here we go. And in the same way, in the negative t direction for its tangential component, it's minus 6.46, so parallel to the t direction. Hopefully I can draw this. And this is a pretty large vector right here large in respect to this 0.22 meters per second. So this component here is 6.46 meters per second. And now the final velocity vector of this right here, if I want to combine this or do some sort of vector algebra, right? Something you learned a long time ago in calculus, and you're like, man, why do I even need to know this? But still, it's a value right here, and I have something. Hopefully this will work out. Yeah, that looks all right. Oh, I can live with that. Okay, I can live with that right here. And I have here, I have essentially, I have combined it here. Let's say I drew this a little bit better. Bam, right here. And this is VA prime after impact. I already know what the magnitude is. The magnitude of this is about 6.47-ish. Okay, 6 meters per second, right? Maybe we'll round up so that I can cover up my indiscrepancies with this. Anyway, right? And I have to work out the geometry here. So I knew that this. Let's see if I draw a horizontal. This looks almost horizontal, but it's not. Um, let's see. I have a horizontal over here. Let's put the horizontal. It will be. Does that look horizontal? Yes, right there. This was theta A, okay? This 512 blah, blah, blah business right here. And let's see, I can calculate, let's see if I can do this in orange and not get this too sloppy. I can calculate this angle right here, this angle, so right here, this orange angle, okay? Orange angle, which I will call, let me just call it alpha. Alpha, alpha is equal to tangent inverse of the opposite, which is 6.46. So this side right here is 6.46, just like that, divided by 0.22 meters per second. And that is, which is 88.05 degrees, and that makes, oh, this is gonna get dirty, this angle right there, that angle, 90 minus 88.05, 1.95 degrees. And really what I want is the angle from the horizontal, right? So I can draw this finally here. This angle right here, okay? If this is a 5, 12, 15, you can, work it out. And this theta A, if you calculate the angle here, this angle right there, this theta A is, it'll come out to 67.38 degrees. And that makes this angle right here, 90 minus theta A, which is this aqua blue-ish kind of weird looking color, is, oh gosh, 90 minus 67.38. Did I calculate this before? It's 22.62 degrees right here. And that makes finally this theta A prime, which I will in purple. Wow, going through the whole spectrum of colors. This angle here in purple, theta A prime, finally is this. Let's see here. It's 22.62 degrees minus 1.95 degrees, and that is 20.67 degrees. So that finally, if I want to describe what my vector VA prime is, it has a magnitude of 6.4, 6-ish. Oh, I wrote it over there. 6.7, 6.5. Don't judge me. Judge yourself. Meters per second at an angle from the horizontal here, not drawn to scale, but accurately 20.67 degrees. Even though this drawing is obviously not to scale, this 1.95 degrees looks a lot smaller. I should have drawn the 6.46 longer, but who knows right here. This VA prime is 6.46 meters per second at an angle of 20.67 degrees from the horizontal right here in that direction. And now we can do the same for B. And in B over here, again, I can go do the same deal right here. I've got this, gosh, let's see if I can draw this a little bit better. I got this, the tangential, the normal component of B after impact is 1.92 meters per second this way. Okay, bam. This is 1.92 meters per second in the positive normal direction right there. And then I have a 2.77 here, a little bit longer, 2.77 meters per second. Do I really need to go through all this for you? You know, you could do it. I believe in you, okay? And I'm gonna give you an answer, and hopefully you will check it for me and you'll tell me, yes, you're right, or no, you're wrong, and I'll say, okay, great. Okay? And this should be a little bit this way, like that. It should be a little bit more this way right here. And the horizontal should be something right about here, right about there. And this VB, this would be VB prime. And VB prime, if you go through the same process and work out all the geometry again, just, a bunch of vector stuff and geometry, all right? VB prime, whoa, what do I need? I don't need that, right here. This ends up being 3.50 meters per second at an angle, which generally to the right from the horizontal at 12.10 degrees right here, right? It's like I'm giving you homework on YouTube. Are you going to do it? I don't know. Okay, maybe you will. All right. All right, and there you have it. Check my work. Is it right? Like it, don't like it, subscribe, judge me, judge yourself. All right. See ya next time.